Algebras, and welcome to your Chapter 3, Lesson 2 notes, where we are going to identify types of functions. And we're going to identify those types of functions based on what their equation looks like and what their graph looks like. Okay? So here are the types of functions we are going to be identifying. Linear functions. You may also know them as lines. Absolute value functions. Quadratic functions. You may also know them as parabolas. Square root functions. Exponential functions. Cubic functions. Cube root functions. Step functions. And piecewise functions. So there are 9 types of functions that we need to be able to identify based on their equation and their picture. And this is just something we're going to have to be able to do. There's really not notes that you're taking for this. It's just looking at the equations and the pictures, and then the homework will be matching those things up with the correct thing. Okay? So let's start with linear functions. They're lines. So linear functions on your graph will have positive slopes, negative slopes, or zero slopes. Like this line has a zero slope, it's horizontal, right? A negative sloped line is just like this one right here. And let's say I had a positive sloped line look like this. There's a positive sloped line, right? Those are all considered linear functions. What's not a linear function is a vertical line, right? So vertical lines are not a function. Okay, so kind of keep this in mind right here. And we did just learn that on the last lesson that vertical lines are themselves not functions. Okay, so just kind of keep this in mind that we are not going to have any of those when we talk about linear functions. Okay, because the no x values repeated for functions. So with all of these things that we look at, we don't have repeated x values. Now, the equations of functions. Here's the most basic looking linear function. It's y equals x. When it comes to linear functions, the only things you're doing to your x are putting a number in front of it by multiplication or adding or subtracting a number behind it through adding and subtracting, right? Linear functions are kind of the most basic looking equations, all right? When we talk a little bit further in lesson 4, you'll understand that this and this, the F and the G here, they're just placeholders for Y. I'm just showing you that in this lesson right now, just so you can see it visually, but we'll learn about it in lesson 4. Okay, so this is just like naming this function F and naming this function G. But if you look at the X's, those are very basic, just being multiplied by a value or a value is being added from it and subtracted from it. Okay? Versus absolute value functions. Now, I love absolute value functions because absolute value is A and V for your first 2 words, right? So A's, oh, hold on one sec, guys. Oh, you're fine. Hold on one sec. All right, guys, sorry about that. And we are talking about absolute value starting with A and V. And if you look at the graphs of absolute value form V shapes or A shapes. Absolute value is basically 2 lines that are meeting at a vertex. And so because these are straight slopes that are meeting at that vertex, and they're just 2 slopes going in opposite directions like this, and meeting at that point, and then going back the opposite direction, they end up forming those A's and V's. So you can always look at those on the graph and think, oh, A or V, absolute value. Now, absolute value has bars, straight up and down bars, that are around your X value. So in your equation for absolute value, any of these equations, you'll notice that the bars straight up and down around the X that's indicating that this is going to be an absolute value graph. Okay. Now, again, I just want to point out, and I know this will be later in lesson 4, but I just want to point out that this is function notation. I've just named this function h instead of putting a y there. And I've just named this function f instead of putting a y there. Okay, so these are just placers for y. So it's still a y equals the absolute value of x minus 3. I can just refer to that as function h. Okay, that's why that looks the way that it does. That's the reason it looks the way that it does. Okay, so absolute value, A or V shape, linear functions, straight lines, everything but vertical. Quadratic functions are next. So quadratic functions also have a vertex. That vertex is a maximum or a minimum. Quadratic functions are parabolas, so the other name for it, right? So you might see or hear me say this, parabola. And I like to refer to my parabolas as smiley faces or frowny faces. And when we learn more about quadratic functions in chapter 11, you'll understand why I like to refer to them as smiley faces and frowny faces. But that's the reason, there will be a reason, and it is actually kind of how you're looking at them, right? Oh, this is U shape right side up, U shape upside down. It kind of makes you think of smiley face and frowny face, right? Parabolas, quadratic functions, have the highest exponent on their x as an x squared. So to have a quadratic function, one of your x's has to be squared in your equation. So the basic quadratic function is y equals x squared. Notice nothing else, around, but you could end up seeing something like this where you've got x squared minus 4x minus 5. But notice the biggest exponent on our x is an x squared. In order to have a quadratic function, x has to be squared, and that has to be the biggest function, or the biggest x exponent in your equation. So notice all of these equations have an x squared in them. These, again, function g, right? So this is just in place of y, all right? And I'm just naming this function g. This is just in place of y. I've just named this function h, right? So that's just in place of y. But that's the same as having y equals negative x squared plus 5x. Okay, so has to have an x squared, right, for the quadratic function. Okay, square root functions. Here we go. X has to have a square root taken of it. So x, you will find, is under a radical symbol. I like to call that a radical symbol too, and you'll learn about that in chapter 9. But this is a square root symbol. And when x is under the square root symbol, it forms like half of a parabola on its side. Okay, that's what you're going to see by this, half of a parabola on its side. And it kind of makes sense, right? Because the opposite of squaring something is taking a square root. So if I want to turn this on its side and only have half of it, then what I'll do is I'll put a x under the radical. And then that way I've only got half of it. Because if I had the full thing, it wouldn't be a function anymore, right? If I turned the full parabola on its side, it would no longer be a function. You'd have repeated x values. But if I turn it on its side and only use half of it, then I've got a function still, and it's considered a square root function. An exponential function will have some base here, and the exponent is x. Notice exponential function, exponent is literally a word. Exponent is literally a word in that. It's an exponential function. So x is what changes. The exponent is what changes in an exponential function. Exponential functions are really cool, and we'll have a whole chapter on them, chapter 12. But what's really cool about an exponential function is that they're extremely rapid increases or extremely rapid decreases. Okay, so here's an extremely rapid decrease. Here's an extremely rapid increase. exponential growth or decay, which we'll learn more about later, is meaning it's extremely quick. Okay, it's very sudden as far as your change in your exponent goes on your graph. Okay, so that change right here, the x change, is what makes this graph jump more quickly, or in this case, jump down more quickly. Now you'll notice that both of these graphs are kind of like leveling out at some point. So then there's this point where they like kind of level out and go on and on. This is a really fun word. Okay, this is like an invisible barrier that your graph is heading towards, but not touching or crossing. And this word is, I'm going to spell it out first, and then I'm going to pronounce it for you. This is what we call an asymptote. An asymptote, right? And an asymptote is an invisible barrier that your graph, your function, your relation, whatever it may be, cannot touch or cross. But it's approaching it. It's getting closer and closer and closer and closer without actually touching or crossing it. Okay? And that's what's happening here. Is this part of the graph is coming closer and closer and closer and closer to the x-axis, to a y value of 0. Okay? But it's never actually going to have a y value of 0. And when we study exponential functions in more depth, we'll talk about asymptotes with every exponential function we look at. Okay, so that's the approach. It's getting close to this like invisible border, invisible barrier, but it'll never touch it. And so we'll have to be able to identify when we look at exponential functions in close depth, we'll have to be able to identify our asymptotes. Okay. So, yep, there we go. We're deep in now. We're 5 in. Now we're on to cubic functions. And with a cubic function, the highest exponent present on your x is going to be a 3, a cube, right? We're cubing our x. And I know I didn't put it here, but you could have something like y equals x cubed minus x squared plus x minus 1. You could have something like that. But notice, what's the highest exponent present? A cube. It forms this shape. That's kind of like a vertical snake on your graph, right? It might do this, okay, like be real loopy, okay? It could do that. It could just do like a mini loop like this guy. But that's what a cubic function will always do. And again, the highest present exponent is an x cubed. So notice this has to be a cubic function, even though there's an x squared that might make you think, oh, quadratic. Because the x cubed is present, you go with the cube, right? Because that is present, it's got to be a cubic function that is happening here. Okay, so it's the highest present exponent on your x that determines the type of function you have. So just like with a quadratic function, you had kind of the matching square root function. With a cubic function, we have a matching cube root function. With cube root functions, if x is under a radical that has a little index here of 3, so a little 3 put on that radical, then it's going to form what I'm going to call a horizontal snake, right? So it does this little thing. Okay, just like that. You just have to be able to identify that and put it in your graphing calculator to graph it. You do not have to do this on your own. When you get to Algebra 2, you'll do more in depth on cube root functions and cube root relations, because some of them are. Some of them are not functions, and you'll see that in Algebra 2. But you don't have to worry about it right now, other than being able to look at it and say, oh, look, that's a sideways snake. So that's a cube root function right there. Okay. Same kind of thing with these things called step functions. As of right now, you just need to look at the graph and call this a step function. Okay. And again, you're only going to have to identify this. You're not going to have to evaluate this. But if you see what looks like absolute value bars with either feet, so these little feet, or hands like this, like on top hands, right? That's a step function. And that's all you have to be able to do is look at that and say, oh, look, that's a step function. And the reason we call these step functions is it looks like you're stepping up a graph like this, right? They are still functions even with this, because if you look, if you draw that vertical line, yeah, this is a dot on the vertical line, but this is an open circle. That is not a point on the vertical line, which means this thing is still a function. These are still functions. And since they look like steps up and down a graph, you just call them step functions. And again, feet on the floor or hands on the ceiling, that's all you need to know. Is if it's absolute value bars that have feet or hands. And I just call them that because if I'm thinking of like a stick figure, that's what they kind of look like. So feet and hands. So if your absolute value has those little extra juts, then you've got a step function. We're almost there. I promise. We're almost there. Piecewise functions are our last ones, and they are literally pieces of different functions on the same graph. Okay, so these are just pieces of different functions on the same graph. We will talk about piecewise functions and graph them later on in chapter 4. And then again, I believe in chapter 11 when we're graphing quadratics. But piecewise functions are just multiple pieces of different functions that are all on the same coordinate plane. Their domain, which is this list right here, determines how far they go. So this determines where you start and stop. You'll notice for a piecewise function, there's two functions with one y, or 1, 2, 3 functions with one f of x. Okay, so, and again, this f of x is just in place of a y. It's just a sub for a y here. So I can name this function f, and I can say, oh, do function f. It was just like naming a child, right? Same kind of thing. Okay, so I can reference this a little bit easier. So if I told you to graph function f, you would graph this piece up to this x value. You would graph this piece between these x values, and you would graph this piece from this x value on. And that's what a piecewise function looks like. Look, I've got this piece, oh, stopped, started this piece, stopped, started this piece, stopped, started this piece. It's multiple pieces of different functions that are on the same graph. That's a piecewise function. Here's another example of a piecewise function, right, where it's partly a quadratic and then a line. And you can see in the equation of this function, now notice it's 1f of x and 2 pieces. So that should indicate to me that this is a piecewise function right off the bat. Then what I did was I graphed this piece up until I got to an x value of 1. So I graphed, boom, I got to an x value of 1. I put my open circle, and then I stopped graphing that piece, and I started graphing this piecewise function. So this one, oh, it would start at 4, and then I'm down to right 1. So there's my first point, and then my next point down to right 1, and then down to right 1, and there you go. And that's how I create my next piece. So piecewise functions, you can see that this is a quadratic and a line, and that's what I then have is a piece of a quadratic stopping here, a piece of a line starting here and going on. That's piecewise functions. All I am asking you to do for homework, guys, is identify these 9 types of functions. So these 9 types of functions, just identify them in the matching activity homework I gave you. I gave you 9 graphs. Write out which type of function each of those graphs is representing. Use these notes. Look back at these pictures. Oh, look, a line. That's a linear function. Okay. Oh, look, a V-shape. That's an absolute value function. And write out the function names, please. Okay. There's some descriptions, and they'll be like, descriptions of the graph, and then name which function they go with. And then there's some equations like these are listed. Look at the equations and match them with the type of function they go to. Go back and look at each of these. I list these here for a reason to help you identify those on your homework, because all you have to be able to do right now is look at an equation and say, oh, that's a quadratic. oh, that's a cubic based on what you see. Okay, so look back at these notes as you do that matching homework. And that's all it is those matching pieces. Okay? All right, my fine friends, I think you've got this, but if you don't, please ask me about it. That's what I'm here for. And otherwise, I shall be seeing you for domain and range next. So, yay, we get to start talking about those X values and Y values being used in our functions. It's very exciting. All right, I will be seeing you soon. Have a wonderful time with your matching activity. Bye, guys.